compared to the size of the overall atom, right, is tiny, right? It's extremely dense. It's almost all of the atom's mass located inside that very, very tiny area. And a pea-sized nucleus would have so if you took a nuclear material and scaled it up to the size of a pea, it would weigh about 250 million tons. All right? So Rutherford's atom left one problem. If hydrogen's got a mass of 1, then helium should have a mass of 2, right? I'm going up from 1 proton to 2 protons, but its mass is 4. Right? So what the heck is going on? Where is this extra mass coming from? It wasn't until 1932 that James Chadwick discovered the neutron, and that solved the mystery. So the extra mass in the nucleus is made up of neutrons. Right? So we got 3 different subatomic particles. Our composition of our atom is we've got a proton, which is found in the nucleus, a positive charge equal in the magnitude to the electron's negative charge. We've got electrons, which are found on the outside of the nucleus, and those guys are negatively charged. We've got neutrons, which are also found in the nucleus. They have no charge, and they have virtually the same mass as a proton. They're a little bit heavier. And in modern physics, we know that these particles are made of even smaller subatomic particles. Right? So protons and neutrons are made up of, protons are 2 up quarks and a down quark, and a neutron is 2 down quarks and an up quark. And so we've gone smaller and smaller and smaller. But for us, protons and neutrons and electrons will be sufficient. Right? So let's do some comparison of our subatomic particles. So we've got our electron, our proton, and our neutron. Right? So our electron is 9 times 10 to the minus 28 grams. And our protons and neutrons are roughly the same, 1.67 times 10 to the minus 24. And you notice that this electron is 4 orders of magnitude smaller, so 10,000 times smaller. Right? We can put this in terms of atomic mass units. We'll talk about atomic mass units later. The charge in coulombs on an electron and the charge in coulombs on a proton are equal but opposite. And if we scale that up to an electron charge, it's -1 and +1. We're going to primarily work with our electron charges here of -1 and plus charge. The charge of a proton is opposite in sign but equal to that of an electron. So looking at our atomic numbers, so some of the other terms that we want to work with is atomic number. We're going to give that the symbol Z, which is the number of protons in an atom's nucleus. This is what makes an element a particular element. So carbon is going to have the same number of, all carbon atoms are going to have the same number of protons. All helium atoms are going to have the same number of protons too, right? It's equivalent to the number of electrons around the atom's nucleus. So you want to, in most atoms, maintain charge neutrality. We'll talk about what happens when you put in extra or take away electrons. But most neutral atoms are going to have the same number of electrons as they have protons. So if you've got 12 protons, you're going to have 12 electrons. If you've got 130 electrons, you're going to have 130 protons. Right? Your mass number, A, is the sum of the number of protons and the number of neutrons in an atom's nucleus. Right? So those electrons, because they're so light compared to the protons and neutrons, we don't even consider them. Okay? We have what's called an isotope. So isotopes are atoms with identical atomic numbers, but different mass numbers. So example, carbon-12 and carbon-14. Carbon-12 has 6 protons and 6 neutrons. Carbon-14 has 6 protons, and it's got 8 neutrons. And when you talk about doing carbon dating, you're looking at the ratio of those 2 isotopes. You can do all kinds of cool things with isotope labeling and description. So a lot of the biochemistry that they figured out early on was doing isotope labeling. So they would take, either deuterium, and they would make like deuterated bacteria, or you might take like some carbon-14 to label some stuff, and you can see how the body machinery takes a given chemical input and produces an output. So metabolomics will oftentimes use carbon isotopes. So allotropes are molecules with the same molecular formula but different structure. Right? So an allotrope is not to be confused with an isotope. Right? Coal and diamond are allotropes of carbon. All atoms have the same components but different chemical properties. They're caused by differences in the number of electrons and by the arrangement of electrons. Electrons of different atoms intermingle to form molecules. The degree of interactions of an atom is determined by the number of electrons it possesses, particularly, as we'll find out, those outermost electrons in what we call the valence shell. So the guys on the outside, and we're lazy and we're superficial as chemists, the guys on the outside that matter and are doing all the work. All right? So isotopes. All atoms are not identical, so Dalton was wrong in this. Isotopes have the same atomic number, Z, but different mass numbers. So here we've got sodium, Na, so we've got our atomic symbol, right? And we've got our atomic number, and then here we've got our atomic mass. Right? So this is our Z, 11 is our Z, the number of protons. 23 is our mass number, which is the number of protons or neutrons. So that's a real quick math to figure out how many neutrons we've got. Right? So here are two isotopes of sodium. So we take our sodium 23 and our sodium 24, and we zoom on in, and we look at the nucleus. Our sodium 23 has 11 protons and 12 neutrons, giving us a total of 11 plus 12, 23. And over here, sodium 24 has 11 protons and 13 neutrons. So 11 plus 13 gives you 24. Then they're both sodium. They're both going to behave pretty much the same way, but they're different isotopes of each other. And we use a mass spectrometer to separate these guys and figure out, well, what kind of sodium are you doing or are you working with? Right? We got different isotopes of hydrogen. Right? So, for example, we've got hydrogen 1. Right? So its atomic number is 1 and its mass number is 1. So it's got 1 proton, no neutrons. We got deuterium, H2, where you've got 1 proton and 1 neutron for a total mass of 2. And tritium, hydrogen 3, we've got 1 proton, 2 neutrons for a total mass of 3. So there's a little watch with some like little radioactive tritium stuff that lights up forever. So how many protons, neutrons, and electrons are in each isotope of hydrogen is something that you would be able to do and demonstrate for me. Right? So let's do one. Right? So write the symbol for the atom that has the atomic number of 9 and a mass number of 19. How many electrons and how many neutrons does this have? The atomic number 9 means the atom has 9 protons. This element is fluorine, symbolized by F, not Fl. One of the things that students will sometimes get wrong when they are doing their beginning chemistry stuff is they will make up element symbols. Okay? F is the symbol for fluorine. It is not Fl. Fl is Florida, totally different. No, actually, Fl is fluorovium, which is one of those 110 somethings. But we're looking at our fluorine. Right? We're going to give it the symbol F, fluorine. I'm going to put a 9 down here because it's got 9 protons. It is fluorine 19 because the atom has 9 protons. It's also going to have 9 electrons to balance out that 9 protons to achieve electrical neutrality. And the mass number gives the total number of protons and neutrons, which means this atom has 10 neutrons. So atoms want to be electrically neutral. And most of the time, when we're talking about here is an atom, we're talking about an electrically neutral atom. Atoms can be assigned a net charge by either removing or adding an electron. And when you do that, these charged atoms are called ions. You can also have complex ions that are made up of many atoms, but we're just going to talk about regular atoms for now. So if I take an electron on, or an extra electron onto an atom, or I take an electron away from an atom, I'm no longer charge balanced between the protons and the electrons. My plus charges and my minus charges are not equal to each other. Atoms are turned into positive ions when they are stripped of an electron, and they're called cations. So cations are positive. Meow. Considering removing an electron from sodium. So if I take sodium and I take an electron away from it, so I get sodium plus and an electron. So here's my sodium. Right, I've got 11 protons in the middle and 11 electrons on the outside. I take away an electron, and my atom contracts a little bit. I've only got 10 electrons. I still have that plus 11 charge. I've got a sodium cation, a plus 1 cation. Atoms are turned into negative ions when an electron is added. These are called anions, right? Negative anions, right? Negative. So if we consider adding an electron to chlorine, so I take chlorine and I put an electron on it to form chlorine minus, and I've got 17 plus charges in the nucleus because I've got 17 protons. My neutral atom has 17 electrons. I add an electron, it gets bigger. I still have the same plus 17 in the middle from my protons, but now I've got 18 electrons on the outside. Avogadro's number and the mole. So you guys have probably come across Avogadro's number and the idea of a mole. So a mole is a counting unit. It tells us how many of a thing we've got, just like we've got a dozen bagels is 12 bagels, or a score of something is 20, right? Mole of something is 6.0222141 times 10 to the 23rd atoms. So it's a lot of atoms. Why is this number so big, you might ask? Well, part of that has to do with the scale that people were working with, particularly Avogadro, back when they were doing these experiments, right? So you can't get down to an individual atom, right? It's really, really hard to do that with the technology now, much less the technology they would have had in the 1700s, right? So you needed to work on lab scale, right? So they were talking about grams of things, so 18 grams of water, or 150 grams of mercury. So 1 mole of an element is the amount of element whose mass in grams is numerically equal to its atomic mass. Right? So your atomic mass and your moles are definitionally related. They're related to each other by definition. So silicon, 1 mole of silicon weighs 28.0855 grams. So 6.02141 times 10 to the 23rd molecules of silicon weigh 28.0855 grams. All right, so what this does is it gives us a reasonable, measurable amount of stuff to work with to tell us about things that are happening on the molecular level. It's just that this conversion factor is really big because atoms are really, really small compared to a gram of stuff. So here is some representative 1 mole's worth of stuff. In class, I would ordinarily pass around 1 mole's worth of stuff. So 1 mole of gas takes up about 20 liters. So 1 mole of sulfur is about a good handful. So you're talking about a handful of most stuff. When you look at some of the things on the periodic table, you will notice that their atomic masses are not necessarily going to be nice even numbers. So for example, carbon, and if you look at carbon on the periodic table, it says that its atomic mass is 12.01 atomic mass units. Atomic mass units are also sometimes called Daltons, dA, capital D, lowercase a. And that's because when you look at the periodic table, it's reporting atomic masses that are based on the naturally occurring abundance of those elements. So in nature, 98.89% of carbon is going to exist as carbon-12, which has 12 atomic mass units by definition. Right, so we're basing all of our atomic masses around carbon-12. Carbon-13 is 1.1% natural abundance, so that's got a mass of 13.0034 atomic mass units. Right? Carbon is really, really important because the mass of 1 atom of carbon-12 is defined to be 12 atomic mass units. This is the end for this. There are some extra slides that are available to you on the handouts if you want to look past them. Extra information you are not required to learn that.